Here we go. Now, here are 6 different molecules. And for us to be able to do this, we need to do the Lewis structures before we can practice this idea of polarity with them. All right? So luckily for you guys, I have already done that. I've already done the Lewis structures. So let me get down to them and we'll pull them up for us to look at. So first one is silicon dichloride. Okay? So first thing with silicon dichloride, we need to have polar bonds. Okay? If we don't have polar bonds, we're probably not going to have a polar molecule unless we follow rule number 1. Rule number 1 says if I have unshared pairs of electrons on the center atom, it has to be polar. Okay? So the first thing I'm going to do here is I drew silicon dichloride, and I'm going to grab my highlighter tool, and I notice right away, there they are. I have an unshared pair of electrons sitting right here on my atom. Okay? So geometrically, this thing really wouldn't be linear. It wouldn't be. It actually would have a kink into it that would actually kink down, and the chlorines would actually sit low like this geometrically. Okay? Because of this unshared pair of electrons here, this is going to be a polar molecule. Okay? So we know that because of this unshared pair. So this molecule is polar. All right? We don't need to do any other work. Because of this right here, this unshared pair of electrons, we know right away it is polar. That's our first one. Now, we go down to sulfur trioxide. Sulfur trioxide looks like this, all right? So in this case, we have, 1, 2, 3 bonding areas. There are no other unshared pairs of electrons on the sulfur, okay? So we have nothing here. Rule number 1 is not being applied. Rule number 2 talks about is everything symmetrical, as you have symmetry there, okay? So it looks like we have oxygen, oxygen, and oxygen. So all of those bonds are going to be the same. Let's check to see if that bond is even polar, because that's kind of important for us to check. And if I look, sulfur is a 2.58, oxygen is a 3.44. The difference between those two things is more than 0.4. So yeah, potentially these are polar bonds, okay? So looking at this, we do have polar bonds. So we do have a pulling effect in that direction, a pulling effect in this direction, and a pulling effect in this direction. But everything is symmetrical, okay? So even though we have polar bonds, so the bonds here are definitely polar, for sure. But the molecule here is nonpolar because we have symmetry. Because everything on the outside, these are all the same, equal, 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 pulling in 3 different directions, okay? So we have a symmetrical molecule. This is a nonpolar example, right? Now we go down to methylamine. Now methylamine is a little bit more complex looking formula. You might think, oh no, but really if you look at it, the thing is kind of easy actually. You have a CH3 group right here attached to an N2 group right here, okay? Now, we have some unshared pairs of electrons here. That's worth noting. If we make carbon our center, which is probably the best idea here because it's the thing has 4 bonds coming off it, potentially we could be nonpolar, right? Because we have 4 things coming off it. However, of our 4 things, we notice that nitrogen is not the same as our hydrogens, okay? Which means if we have a polar bond, so if this bond is polar and pulls it in this direction, we probably have a polar molecule. Well, let's check that. Do we have a polar bond here? We go back to our periodic table. Nitrogen is a 304. Carbon is a 2.55. Okay, 2.55 to 304. Yeah, that is greater than 0.4. For sure it is. So in this case, we have a polar bond there. With a polar bond, we now have a polar molecule. So in this case, we'd have polar bond right here, and we have polar molecule. Okay? Because we do not have symmetry, we have polar bonds, okay? And we have this shift of electrons in this direction. So if we were to then write up what is our polarity on this, make this a little bit bigger. we could say that this side, because we're going in this direction, that this side is going to be partially negative. This side over here would be partially positive in this molecule, okay? So this would be the symbolism we would use to show partial negative, partial positive. This symbolism here is to show the bond, okay? So the bond is pulling it in this direction. There's nothing to oppose it, so we end up being partially positive, partially negative, and we get a polar molecule. Let's go to our next one. So we have C3H8, okay? So C3H8 is propane. You guys have probably heard of propane before. And now we take a look at our molecule. And first thing I'm going to look at is, okay, well, carbon to hydrogen, these bonds are all nonpolar. So if we go back and do our math between carbon and hydrogen, the difference is less than 0.4. So these are all nonpolar bond. The carbon to carbon bonds are nonpolar. Okay, so far, everything in here is nonpolar. Okay. So all my bonds are nonpolar. I don't have any unshared pairs of electrons on this. And everything is symmetrical too, right? We have all these hydrogens on the outside. In here, these are all nonpolar, nonpolar. There's nothing here to create polarity, okay? So because we have all nonpolar bonds, because there's no unshared pairs of electrons, because we have symmetry, this molecule is definitely nonpolar. So we have a nonpolar molecule here. All right, let's go on to our next one. This one we've already actually done. It was one of our examples from before. So here we look, we have a carbon to chlorine bond. And if we look up that bond to make sure that if that's polar or not, carbon is a 2.55, chlorine is a 3.16. So our difference here is polar, it's greater than 0.4. Carbon to fluorine, we've already done that one. 2.55 to 4, that difference is greater than 0.4. So that one is also polar, okay? So we have two scenarios here where we both have polar bonds, all right? So let me draw this up. So we have pulling in this direction, and we have pulling in this direction. But the fluorine ones pull greater in this direction and in that direction. And because we know this is three-dimensional, and it is not a 2D molecule, where these cannot be opposites of each other, we do not have symmetry here. This side here is going to be less than this side here. So we're going to end up getting a partially positive side here, a partially negative side here, because the blue is pulling stronger. So this is a stronger pull in this direction, and we're going to get a polar molecule. So this is a case where we have polar bonds and a polar molecule, both in this case. All right, last example. We put this one in here on purpose because there's something very unique about this one, okay? So in this case, we take a look. We have, first of all, should come to mind, or something that kind of stands out, is we have a -2 charge, okay? We see the brackets. That reminds us that this thing here is part of a polyatomic ion, okay? So to be honest with you, what's going on the inside, we could care less about, all right? Because we see this right here, okay, that means it is an ion. If this is an ion, polarity is off the table. We don't even talk about polarity anymore because it's charged, right? This entire thing, this entire molecule itself as an entity has a -2 charge. So this entire thing floats around in the world with a negative charge to it, which means the entire thing is negative, which means it's always going to act like an ion. So in this case, we wouldn't even talk polarity. We would ignore polarity, and we would just say, hey, this is an ion, okay? So we would identify it as an ion, and that is how we would discuss polarity of this. This whole thing is negatively charged. It's an ion. That is what it is, okay? We don't care if one side is more positive, one side is more negative, because the whole thing together acts like a negative big ball of negativity, okay? So that's the last one. We want to make sure we put that one in because it's actually a really easy one, but if you didn't know for sure or didn't know what to do with this, that -2 charge, you now do. And that's how you would handle anything that has a charge on it, it's already considered an ion, and then you don't even deal with polarity with those. All right, everybody, those are 6 great examples. We do have more examples and more practice that you can do in your student files for you. But if you have more questions for me, let me know. Thank you.